Welcome to the Data Science Speaker Series at the University of San Francisco. The speaker series is sponsored by the Data Institute, which is the umbrella organization for all data science, data engineering programming that happens here at the university, which is very cool. Our speaker today is someone that most of you know well, Unet Interian. Is an associate professor in the MSDS program, so the Master's in Data Science program. She holds a PhD in applied mathematics from Cornell University. After a postdoctoral fellowship at UC Berkeley, she worked for 5 years as a data scientist at Google. Unet co-founded Aqualab, a startup that helped organizations develop data-driven products using machine intelligence, and she has designed data science courses for both UC Berkeley and USF. Today's talk will be about convolutional neural networks, CNNs, used for image segmentation, utilizing the PyTorch framework. We'll construct a pipeline for training Unet models from scratch and fine-tuning pre-trained models. Plus, we'll introduce the albumentations library for data augmentation, which adds another layer of depth to our exploration. I didn't write that. Anyway, enjoy, and I'm going to hand it over to Unet.
Hello guys, can you hear me? Can you hear me? Yeah, okay. Thank you for being here before the most difficult work load of this module. So, okay, let's see. Okay, good. Okay, so in this last seminar, we're gonna have these seminars. We had the seminars about deep learning. In this last seminar, I wanted to introduce you to segmentation as a task. So what is segmentation? And I'm gonna show you some other pictures, but I just wanted to start by telling you about one problem in which segmentation is very helpful, and then to kind of tell you why are we doing this? Why do we want to do this? So in medical data. When you have, for example, we could have a tumor, okay? They are seen by the doctor, and then they may have radiotherapy, for example, right? So, and before having that, you have to get a scan of the body, okay? And you have to either make a contour or actually just put pixels everywhere where there is an organ, okay? Because what you want to do is that you want to put radiation on people, but you have to avoid organs at risk. Does it make sense? So in general, a doctor would go and have to by hand, basically, a doctor or a doctor in training, but people that get paid actually a lot of money have to go and draw these contours and basically make sure they're good so that then they can plan these radiotherapies, right? Like a lot of us, some of us work with UCSF professors. Some of them, that's what they do for a living. It's like kind of the part of what they do is that they plan this, they plan the machines that will do this radiotherapy. Okay. So, anyways, this is one of the cases in which all of these automatic models are very good at going and making these contours or segmenting those images. And then that will save a lot of time from doctors, right? So that's kind of one of the applications. I'm going to show you another application. Another way to think about it is that, so you have a car, like a self-driving car, and that self-driving car has a camera. And one of the things you have to do is that you have to divide the image in pieces to understand, what is a human, what is a building, what is a sign, what is a road, right? And that also comes from something like that, this segmentation. So this is related to many different applications that are very important in medicine, in self-driving cars, and in many other places, okay? I actually work with one company as well. They were trying to do a medical device that will detect that there was a problem. So there is an operation, you put a fake thing on your eye, right? And you wanna, get a bunch of images and automatically detect if there is a problem with the operation. The operation is quite expensive. There are not many doctors that do it, So they were trying to build an application in which you would do that automatically. And underneath, what you're doing is segmenting images to figure out something is not too big or something is not too small, and understanding, basically, measuring the likelihood of being a problem, right? Because if there's no problem, it's all good, but if there is a problem, maybe the patient has to fly back to another state where he got the surgery and see the doctor. But if there is no problem, what's the point on him having to fly back and see that? So anyways, so those are things that people do. And let me actually, another thing I wanted to show you before because what I do for a living is just writing code and showing you code. So that's mostly what I'm gonna do today, just showing you code. But before that, I also wanted to show you a picture that I am missing here. Let me see if okay. So, I am not gonna get in the details of this model that much, but I just kind of wanted to show you a little bit of the architecture and the type of model that we're gonna look. So, what we have is an input image, and what we wanna get out is another input image. The first input image is a regular image, or a 3D image if it is a medical image. And the output image is an image that I'm gonna show you some examples that would give a class to every point. The class could be, so you have a pixel on every pixel it could be like a human pixel or a street or a sign pixel. So every pixel is gonna have a class, right? So this is called an image to image model. So an image goes in kind of this way, and an image goes down, and then around here you start trying to generate the output image. So it's called a Unet model, and it's a convolutional neural network model. This part here is called the encoder, and this is the encoder. And hopefully in one of the future classes you guys know more about this. I just wanted to mention that there are these models in which you give it an image and it will give you back another image, okay? And so your input is an image, the output is an image, and the output you're gonna have a loss function against that output, okay? So for example, you know how when we have 5 classes, we have 5 probabilities, right? So now we have a model that is an image, right? And the output is an image. So every pixel might have 5 probabilities if you have 5 classes, right? Or it may have, in the case that I'm going to show you, 20 probabilities per every pixel because you have 20 classes, okay? So the output might be, I'm going to show you the output, so let me just kind of instead go that way. But I just kind of give you the idea that there is these models that are very cool, that you have an image, they will generate an image for you, okay? And that's what we're going to train, okay? So that's it. Let me bring out this. So the notebook for today is in the same place that I had these other notebooks in this series. It's my GitHub, and then deep learning tutorial or tutorials, something like that. So it's like tutorials. Okay, so let's look a little bit at this code, and so these are all a lot of imports, different stuff that we're going to talk about. And the next thing I wanted to tell you, so this is how we have a data set. This is how the images of the data set looks like, okay? And this is the labels. So what you're seeing here is like every color is a different label. So actually you see colors, but if you actually look carefully at the image, there are 20 different classes. And so if you actually look, it's for every pixel, it's gonna have a class. It's gonna be, every pixel is gonna be a 1, a 3, a 7. So let me actually show you, if I do something like trying to understand the minimum and the maximum of these pixels, the minimum is 0 and the maximum is 19. So that means that we have 20 classes here, And it's just that when I try to show this, it shows you this representation, right? But really, what we have here are classes. Every pixel has a class. Make sense? Yeah, good. So basically, this is the input here, and this is kind of the output here. It's kind of funny. I see. So do you see that? That there is actually, this is kind of like a car. This yellow thing is a car here. It's very hard to see it in the picture, but it's kind of there. Something with the other. Okay. So the first thing, guys, my images are a little bit big. This data set that you can find it here. It's called cityscapes data set. You can find it. Has a lot of different data, and it's very cool. It's yeah, so it's free. You can find it here. So these images are pretty big. So they are like 1024 by 2048, and we don't need images that are that big to train our models, or at least not the first model you have. Especially if you don't have a kind of that many GPUs, or your GPUs are small, you start by looking at images that are much smaller. Okay. So the first thing we're gonna do is that we're gonna resize all the images. And you do that before you start doing anything, right? You can always go back and get the previous version. So I'm going to resize them to 512 by 1024 by 3. So and you resize both the input and the output, right? Because they correspond to each other, right? So you find some, okay, you see my input and output, right? So you resize all of them. Actually, I may have even resized them to even smaller than that. Yeah, so I resized them to even smaller than that, to 220. Yeah. So the first thing you do, again, you resize them, okay? Then after that, I just wanted to introduce you to a library. You know that, right? How, like last time we talked, I show you how to do different data augmentations, right? So why do we do data augmentation? Do you remember that? Because, so if you have an image and you rotate the image a little bit, it's still hopefully having the same label, right? Or if you like maybe blur the image, that might be the same label. So on that will give, by your model, we see different data, right? So hopefully that helps your model generalize better. Does it make sense? So basically, doing the augmentation is very, very important to train image models, right? And last time I actually used to do a very small augmentations that I wrote at some point that are very small. But I wanted today to tell you about this library called albumentations, and it's very, very cool, because it has a lot of different functions that you can use. So for example, here I'm using like random crops, flips, horizontal and vertical flips, rotations, grid distortions, which are very powerful for these pipelines. And you can look at many more. Okay. Also, let me tell you why it's good to use a library. What is the problem you see with the type of task that we have and trying to rotate an image? Do you see any problems with that? Our labels are for every pixel, right? So we have to be very careful. And anything you do to the X, you have to do to the Y. Does it make sense? So it is tricky. I at some point wrote this by hand, before, and it's tricky how to get this right, because you have to treat the X and the Y almost the right way, right? Almost, because, for example, if you want to blur the original image, you don't want to do that to the labels, right? If you rotate, you rotate the same, right? If you rotate too much and you're missing some of the border, whatever you do to the X has to be done to the Y. So it is not straightforward to do this when you are doing segmentation. So it's good that you have an image and you don't do it by hand, okay? So anyways, again, very important that you, if you are doing segmentation, that you either do it very carefully or use a library and you send the X and the Y at the same time. Mm-hmm. Do you see that? Why that might be a problem? So that's kind of very important. So anyway, so this library is pretty cool. And for example, this is what happens if you, at some point this got flipped, so both of them get flipped at the same time. If you move it or whatever, also it's gonna be, if you move it in one direction or the other image is gonna be moved. If you rotate, it's gonna get rotated. So that has to be done at the same time to both of these images. Okay, so the next thing is the dataset. You remember the dataset is where we tell PyTorch how to get your X and your Y, okay? So you have to, the dataset for an image problem is much more complicated than the datasets that we have done so far in school. So anyways, you say, well, what is the path to your data? You pass that and the folder. Whether you're gonna transform your data or not, remember that we transform the training data but not the validation data. Then you pass the transforms themselves as well here. You decide which transformations they're gonna do, and you basically load your files and your labels and so on. And then in the get item is when you tell PyTorch exactly, given a particular index, index 30, basically what X and Y do you want to transform. And notice how you pass both the image and we call it the mask. And the mask, we pass both the image and the mask to the transforms, and you get back both the image and the mask. Okay? So you pass that at the same time. That's how you do it. Okay, so any questions so far? So basically, this is a little bit more complicated than what we have done so far. So anyways, you get your train data set and your validation data set. And these are the shapes of the X and the shape of the Y. So why is the shape of the X 3,256 by 512? Because a regular image is basically, so there is a noise. Is it me? Is it me making the noise? What do you think it is? You think that this is, should I am like, let me try to change this. Okay. Hello. Can you hear me? Yeah. Well, I don't like this. It's like I'm singing karaoke here. But I was very annoyed by that noise, so let's try this. Okay, so guys, why are we doing 3 by 256 by 512? Well, remember that when we have an image, and the images, colored images have like 3 channels, okay? But then PyTorch likes to get the channel at the beginning, okay? So we had to flip it so that the model, that's how the model likes it, right? And then why, what is the Y 256 by 512? Is because the Y is just gonna have a class, right? So it's just basically, let me see if I can show you a Y here. I think this should, okay, yeah, you see, it's running, that's great. Okay, so let me show you what the Y looks like. It's gonna be like a lot of mess, but you see, these are numbers, right? So the Y is a class for every pixel. So basically that's just a two-dimensional. So far for one Y, it's just two-dimensional, and it has the same kind of number of pixels as the X, okay? So let's just cut this. Okay, so we have that. Then I also like to check that both the training and the validation have the same shape. Since I do slightly different things to the training and the validation, the training goes through this random transformation, but the validation just goes through a center crop. So I like to test that both of them look the same. And then basically, how many images do we have for training? We have almost 3,000 images for training and 500 images for validation. Okay, then we have a data loader, which we have talked about. This is how we train models in batches. Remember that when you have an image model, it's very important to train in batches because your data is not going to fit into, at least it doesn't fit the GPU that I have to use, right? So you need to load just the amount of data that you can feed on the GPU at a time, because otherwise you get out of memory errors, okay? So on how you figure this out is just by running the model. If you get out of errors, well, you're out of memory, and you try to figure out by lowering the amount of the amount of images, the batch size, how many of them you can feed. I am going to show you some other tricks later on this class on how to save memory. There is something called mixed precision training that helps you to save memory later on. But one trick at a time. So I'll show you this later. Okay, and this is the Unet model. I don't want to actually spend too much time here because this is a little bit complicated. So you see there is like some convolutional block. It's a bunch of convolution block. And then there is the encoder, it's a bunch of different blocks. And then the decoder is using something called transpose convolutions. And this takes by itself some time to explain. And the forward you see is like this one here. But you can see that, this is the whole model, guys, right? Like, I mean, if you have some time and people explain what a convolutional neural network is and what a transpose convolution is, you can read this code, right? It's not a big deal, right? There are other codes that are, other models that are more sophisticated, and I'm not going to show the code, but this kind of basic model, you can understand this with a little bit of time, okay? Okay, so there are all the details here. The data set came with some class weights, and this is just basically your loss function. Instead of being giving the same weight to every class, it's gonna give some weight that is different from different classes. And don't worry too much about it. It's just like a way maybe to balance your data a little bit better, because if you have one class that is a minority, it might not train that well. So, that's how use weights just sometimes to fix that problem, to fix the balance problem. Like if you think about, if you're trying to predict the road might be very easy to predict because you have so many pixels that are road, right? And it's so simple, it's a road. It's very simple for an algorithm. But maybe a human next to a tree might be difficult. Maybe a human just like takes less space, less pixels. So it might be more difficult, right? So you might want to give more weight to the pixel of the human, also because it's more important, right? Than to a pixel that comes from a road. And how you do that? Well, you try to play with the weights for every class, right? So anyways, just keep that in mind. It's something that you might want to do at some point. So and which is our favorite loss function for the homework? For the homework for multi-class classification. So why do we have a multi-class classification problem here, right? So think about it, every pixel belongs to a class, just to one class, right? And the probabilities of every class have to sum to 1 because a pixel just can have one class. It's either a pixel of a human or a pixel of a road. It cannot be a pixel of a human on the road, or at least not the way we think about it, right? So every pixel has one class, so this is a multi-class classification on every pixel on that image, right? So we use like F dot cross entropy. Okay, so anyway, so we just, before we do anything, remember, we just try to make sure our model kind of works and we can compute some loss function, okay? So what about computing accuracy, right, guys? So this is the shape of my y hat. What is this one for? That's the batch size. When we have a batch size of 1, so we'll get a 1 there. What is the 20? We have 20 classes, right? So that's where the 20 is gonna be, right? And these are just all the pixels. Okay, so we're gonna have 20 things, 20 probabilities for each pixel, right? So that's how this works. And basically, so how do I get a hard prediction on this? How do I know which one of the pixels, which one of the classes are going to correspond to that? So we take the maximum, right, on that particular dimension, on the 20, and we find the class of the maximum. So that's how we do a hard prediction and figure out what the hard prediction for a particular pixel is, right? So basically, you use torch max. You tell torch max on what dimension you want to do the max, and then your prediction looks like this. You see, one class per pixel. Of course, that's a hard prediction. Remember, the soft predictions are going to be probabilities for each one of the classes for every pixel, right? So the soft prediction is more like this thing you saw here. Mm-hmm. So and how do you compute accuracy? Okay, so the first thing is that you compute accuracy. You sum all the pixels that look correct. Okay, but then you have to divide by the amount of pixels, right? Because otherwise, life might be difficult. I don't know about this 3 here. This 3 might not be. Let's see. So you basically, first of all, compute accuracy per image, and then in general just accuracy for all the images in your dataset. So anyways, this is our regular training loop, right, that we have talked about. So note how this is very, very similar to what you guys have done. I have 2 models here. The one I just show you, the model that is the Unet model. That model we are gonna train from scratch, okay? But then I have another model that is a pre-trained model on a segmentation task. And I am going to use that model later on, and I am going to get a better accuracy by using that model later. So I have 2 models that I'm training, and when you see this if pre-trained, this y hat equal, it's just because I have the 2 models, and how I access the y hat is a bit different from the model I wrote to the model that I'm using for training. So and I'm using the same function for both of them. So that's why this is here. But otherwise, this is a regular loop, right? So we have our x, our y. We put everything in CUDA because we're using the GPU for training. We compute our loss with these weight classes that we talked about before. And then, so this is a validation metric function that we have seen before. And then basically we want to be able to compute the validation loss and the accuracy, okay? So, and our training loop again is very, very similar to training loops we have seen before. So we have our data loader, we have X and Y there, we compute our Y hat from the model, and we just kind of do, lost or backwards, optimize it per step. And I am using this TQDM. I don't know if you have seen that. It's very cute. Have you used that before? Yeah, I don't use it all the time, but I like it. I like it especially when my training takes a while. Like I was making sure this morning that this notebook was going to run well, and this takes a little bit of time. It takes like a good training 10 epochs. I think it took at least 40 minutes or something, right? So I wanted to make sure I could finish before coming here. So anyway, so it's good to know more or less, especially when your training takes some time, it's good to know when it's gonna finish. So then, this TQM bar helps you to do that. And and then basically, so this is our training loop. If you have any questions, tell me about it, but this is pretty much what we have done also in the past couple of seminars. So and then, we train, and remember basically, so let me tell you what I'm doing also. So I'm saving, the way you train, especially when your model is a little bit expensive, is that whenever you see a better validation loss, you save it, okay? And the way I like to do it is that I say, well, this is a model that has accuracy of 70, right? And then I get a new model that is better, so I say model 75 accuracy, right? So I save my models because, that this might be expensive, right? So you want to keep the best model so far. So, and I like to print, how is my training loss going? How is my validation loss going? And what is my accuracy, right? Because the accuracy at the end is what I care the most about. But the training loss and validation loss will tell us a little bit that the model is trained the right way. We want mostly the training loss to go down, even if it's not perfect, you see. Well, no, it is pretty perfect in here. Yeah, it's pretty perfect. It goes down all the time. But it doesn't have to go down or go up all the time, right? But it mostly wants to go down, right? And also the validation goes down. And the accuracy goes up. So I trained for 10 epochs with a fixed learning rate. This is not the best way of training. Like we could have done some more sophisticated things, and we can train for longer as well, and most likely get a better result. But remember, this is trained from scratch, right? So, and I have told you enough that you should always try to use pre-trained models as well, because that will give you a little bit of a bump in your accuracy. So the next part of the notebook, I'm going to show you how to use a pre-trained model. This model is from a couple of years ago, when I was doing some research that seemed to be the best model. Right now, there are more powerful models, and I just kind of really didn't have time this time to bring you a model from Meta. So Meta has a very big segmentation model, and I don't know how easy they are to fine-tune, to be honest. So we'll have to go and try them out. But if you guys have a problem like this, remember that the first thing you have to do is to go and research a little bit what are the available pre-trained models for this problem. Are these models kind of close to the task that you are going to try to do? If they're not, don't worry about it. Just still try it, because these models are very powerful. But remember that maybe you might want to try more than one pre-trained model. Okay, let me actually. Okay, so the next thing I wanted to show you, anyways, is how this model makes predictions, right? So this is another image, and these are the predictions. So, it doesn't look that bad, no? So this is kind of a human here, doesn't look, if you actually have to really look at it very well, and there is a human, and there is a bike. And you see the bike and the human much better in the prediction than actually in the image itself, right? So there are some cars, and you can see how a model, a car that is trying to go around a city, these having very good predictions like this might be pretty useful, right? For them to understand, humans and other cars and things like that. Okay, so basically the predictions are just like you make a prediction, probabilities on every pixel, and then you take the class of the highest probability, and that's your prediction. That's what we have done here. Okay, so this one is not just a great prediction. Probably it's not. Okay, so let me tell you about this is supposed to work, but it's not working right now. So there is a way of, and there are like different libraries out there. So this AMP was a library that people were using at some point, but it may be that right now at all libraries, like Hugging Face has a library for half precision or mixed precision. And then, so basically what this like half precision library does is to help you to reduce the size of your model, basically. And I'm not gonna go into details of how it does it, but basically you are saving space in your GPU so that you can train with bigger batches. So in order to do that, you have to do a couple of things. Your input needs to be, you change the type to a half. So instead of a float 32, it's a float 16. So you have to change that. And again, the different libraries you're gonna have to do this in a slightly different way. But what else you have to do? So you have to, you basically just do something like this. You wrap your lost stop backwards into this code. So instead of doing lost stop backwards, you have this code here. And you put half here. And pretty much you are able to just train. I think there's another line of code. I'm gonna find it at some point. So the optimizer is another line of code too. So let's actually. Okay, so you see, so this is another line of code here that you need. So there are pretty much like 3 lines of code that you need to save a lot of memory. So if you're dealing with an image model, you definitely should look into trying to train with half precision because it doesn't really, it saves you a lot of time and it doesn't take that much to do. So, okay, so this is basically training with half model, and it's basically just allows you to do faster training. So now let me introduce you to how how you go about getting a pre-trained model. Okay, so this model at the time that I was trying to understand the space of segmentation models that is called Deep Lab V3. And again, right now I would just go and try to figure out if there are better options than this. And this is based on ResNet is a famous model, and this is based on kind of some ResNet backbone. So don't worry about what that means either. This is just a model that has been, trained on segmentation tasks. So, and basically it's very simple. You just say, hey, look, I need a model that will give me 20 output channels. So notice that convolutional neural network models do not care about the size of your input. How big is your image? Most of them do not care. Some of them are funky, and I'll tell you which ways. But most of them, some of them, they want you to have inputs that are power of 2, or yes, this is very fun. But it's the way the model works. But these are kind of the older models, Unet models. They need you to do that. But most of the more current models, like this one, it just doesn't care about the size of your input. And this is great. So the only thing you have to tell this model is, hey, I need 20 probabilities for each pixel, basically. And then you have a model that is ready to train, okay? Or it's ready to fine tune, remember, because a lot of it comes with weights have been trained already, right? So then basically, then after that, after you have your model, it just kind of, this is, so you had to either import this library or have a file with this model or whatever it is. But after that, or just kind of install the library. But after that, you just tell them how many outputs you want, and then everything else is kind of the same. You train it, and before we got, and this is just 10 epochs again, and a fixed learning rate. Before we got to a model that was like almost 80% accurate, and now by just getting a model trained on some other data and going for 10 epochs, we got an 85% accuracy, which is 5%, which is pretty big. Going from 79 to 5 or 6% accuracy. And again, you can play with this. You can go for much longer training. You can play with doing one cycle training. Do you remember that we talked about the one cycle training that was better than fixed learning rate training? You can also try to figure out if by freezing part of the model, the original model, that kind of works or not. So you can play with this, and this is just kind of really a baseline of the accuracies that you could get, Okay, so guys, I am mostly, this is what I wanted to show you today, and I want to open it to questions about, the code or the applications or anything else that you might want to ask. Yeah.
I'm just curious, I'm not sure what.
Yeah.
I noticed, I think in the 0.9 section, you're using the Adam optimizer.
Yeah.
Is there a particular reason why you chose that optimizer, or is it just
It's a popular optimizer. It's a popular optimizer. Either that one or it's one called Adam W. It's something that just people like to use because it's a good optimizer. But a lot of these things you go with the flow. You see what people are doing. The same with the models. Like you go around the internet and understand. If Meta puts a model out there that is public, probably they have a lot of money and a big team to work on it. So probably try that, right? So before it was all of this came a lot from the research and the universities, and now more and more a lot of the models are coming from companies that have a lot of resources. So on the other hand, if the models are too big, the question is, can you actually train them? And that's another question that we have to do this trade-off between having models that are smallish and we're able to train them. But anyways, it's just to have to understand if you have a particular application, the space around these models and which ones, and the optimizers and all of that. You just friendliness of the internet and see what other people are doing, basically. That's how you do it. So, at least, yeah, any other questions? Good? All good? Yeah.
I'm noticing that the accuracy falls off by the end of it. Like it actually
okay, so the best model is not the model that you, so this one is a previous model and the other model is this one here. The best model is not the model that is the last one, and that's why you save it. You save the model because so you have a validation set. And what is a validation set for? For many things, but one of them is for hyperparameter tuning. One of them, you can let them run for a while, and it might happen that the best validation accuracy you get is in the middle of the training. You save that, and then you use that as your final model. In many cases, it would be the last one as well, because so what happens is that what I show in the last time I gave a seminar is that sometimes we like to use these learning rates that go up and then down. So in general, when you train like that, your last model is the best model in general because your neural rates go down, 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 and you just start moving things very, very small, very slowly. But if you train with a fixed learning rate, at some point you're gonna see that the learning rate is too high for the current model, basically. So you're gonna see that you're gonna get to worse point, right? So in here, I'm training with fixed learning rate, so it's not the best way to train. And I'm training for not very long either, right? So it's better to train for a bit longer. So yeah, just a little bit of a baseline. So we can play with that. So you guys, some other last question? Well, I will be around for a little bit, and I thank you for being here, even if you have many exams next week and a few homeworks too. So see you around. Bye-bye. Thank you.